So, what we're going to do is we're going to talk about elementary particles. Um, we're looking at matter and we're trying to talk about what matter is composed of. Traditionally, we viewed elementary particles as electrons, protons, and neutrons. But when we get a better understanding of some of what some of those particles are constructed of, our list of elementary particles change. So, the first thing that we do is we come up with some terminology. The first one is what's called a hadron. A hadron is any particle that's made up of quarks. So if quarks go into the construction of that particle, it's called a hadron. Okay? So our protons and neutrons are constructed of quarks, and there's a series of other particles like a sigma and other particles, and there's a lambda that are composed of quarks. Okay? So those are called hadrons. Cool? Other particles that are not composed of quarks are called leptons. So composed of quarks, hadrons; composed of not quarks, leptons. And then there's another category that we'll talk about here shortly. Leptons are not composed of quarks. Like in that category of particles is the electron. The electron is not composed of quarks. You may believe it is, but it's not. It's not composed of quarks at all. Muons, which is a short-lived particle that once it enters our atmosphere, it doesn't last very long. All of our neutrinos, those are all leptons. Okay, so you have hadrons and you have leptons. Well, in addition, there's a third category, but we wanted to talk about hadrons, we want to talk about leptons before we talk about this third category. So what we have here is I have them all broken down. Here are my elementary particles for hadrons. These are our breakdowns of quarks. Down here is our leptons. Okay, here's my neutrinos. Here's my other particles. And then we have a third category called bosons. Now, the reason why bosons are not included in these particles is because bosons are different. Okay? These particles are called fermions. If you look over here in the spin category, it's 1/2, which means that they're fermions. And what a fermion is a particle that cannot exist in the same energy state. So when we were talking about Schrodinger, we're talking about energy states, or energy wells, all of these fermions, which are my hadrons and my leptons, can't exist in the same state. They have to have something that separates them, some energy signature that separates them from other particles in order to exist in what we think the same space is. Okay? Bosons, on the other hand, are not limited by Pauli's exclusion principle. Bosons can exist in the same state. And my list of bosons are photons, gluons, and then we have these two weak forces. There's actually a fifth that we haven't been able to detect, but we do believe it's out there, and that's called a graviton. A graviton fits in the boson category. It's also called a Higgs particle. That's what we're looking at the Higgs particle for, because we believe it's associated with the graviton, or it is the graviton. Okay? So we have fermions, we have bosons. We have hadrons to here, we have leptons. Okay? And in my bosons, I have photon. And photon isn't really a particle. I mean, it has the duality that we expect with with mass, with matter. But is it really a particle? I don't know. Okay. The reason why the reason the bosons are here, it turns out that there are fundamental forces in the universe, and the bosons are the messengers. They tell you information. Like when we were talking about Heisenberg's uncertainty principle, we were talking about photons talking to electrons. Well, the photon is a boson, right here. But it's the messenger. So my bosons are messengers that allow electrons to communicate with each other, protons to communicate with each other. So when we talk about fundamental forces, we're going to revisit this idea of these communications. Okay? Cool? So, hadrons, leptons, bosons, fermions. Okay? Now, as you can see, that I have broken up my quarks, which make my hadrons. up, down, charm, strange, top, bottom. And I also have a number at top, 1, 2, 3. Okay? These are first generation, second generation, and third generation particles. Okay? It turns out that first generation are common. They're found anywhere in the universe. As a matter of fact, our two common hadrons, or protons and neutrons, are composed entirely of ups and downs. Okay? Second generation are particles that are formed with high energy collisions. I mean, they're naturally occurring in the way that plutonium is naturally occurring, but it's much easier to create them than to go out in the universe and try to find a chunk of plutonium. Okay? Third generation are even more higher energy objects. They're not terribly common. As a matter of fact, bottom is one of or is it top? It's one or the other. It wasn't really discovered until last decade. Okay, cool. And each one of those particles have properties. Now I'm only keeping track of charge and spin. And spin we need to talk about. But there are other properties like mass, how heavy that particle, well, how much mass it has. And I didn't put it on there for one simple reason. We don't really know if quarks have mass. They have mass properties, but we don't know if they have mass. And as a matter of fact, when you add quarks together in different combinations, you don't get the expected mass value. Okay? So I didn't put them on there. I'm just going to concentrate on charges and spins. And now, talking about spin, when we talk about the spin of, let's say, an up, it can be both positive and negative. It can be an up spin or a down spin. It's just the value of that spin when dealing with an up is a half. Okay? Cool? So you can see that when we're dealing with neutrons and protons, that we can have a half up spin, a half down spin pretty easily, regardless of the combination. Cool? So charges, positive 2/3, negative 1/3 for my quarks. My leptons, as you can see, my neutrinos, have no charge, and they have a half spin. So there's still that fermion. That half spin makes them a fermion. Where my other particles, my electrons, my muons, and tau, are all -1. They have a -1 charge, which is good because electrons aren't made of thirds. Cool? Now, some other things that we need to talk about when talking about these particles is that there's an antiparticle to every single one of these. Okay? Even my leptons have an anti-electron, have an anti-muon. Okay? Cool? But when it comes to quarks, it's an anti-up, anti-down, anti-top. And let me give you an example of what that looks like. So if you're adding something together like an up and an anti-up, an up looks like that. The unit or the notation for up spin or up quarks is just U. The anti of that is a negative U. Okay? And that antiparticle has the exact opposite property as charge. So there's other things that are opposite associated with it, but instead of having the 2/3 charge, that up would have a negative 2/3 charge. Cool? The other thing, so we don't have 6, we have 12. We have up, anti-up, charm, anti-charm, which I'd say would be a bummer, top, anti-top. Okay? It's not top and bottom, it's top and anti-top. Cool? Erase that real quick. So, like I said, it's not that we have 2 or 6, we have 12. Okay? And we actually have more than 12. The other thing, let's take the example of a proton. So a proton, we know, has a +1 charge. Okay? And it has a spin 1/2. So using only our first generation particles, we could make a proton. Okay? So if I go up, up, and down, so my proton is up, up, down. Okay? In order to make that proton, I use 2 ups and a down. Well, we've got issues here. First of all, my spins are going to eliminate. We're going to have trouble here. Okay? If my spins stay up and up, like an electron, I can have an upspin and a downspin. So I'm just going to say that this is an upspin and this is a downspin. That way they're not existing in the same state, hence the problem with Pauli's exclusion principle. But regardless of the spin of the down, it's going to interfere with the other two. So we have to have a way in which we can make this down not interfere with the other two particles. Well, the thing that we come up with is colors. So first of all, a little bit of vocabulary. We refer to these quarks as having flavor. I don't know why it's flavor, but that's what we refer to it. I think it was an attempt to say, oh look, we're cool physicists. These things have flavors. They don't have numerical values. Okay? And then the other thing they come up with is this idea of color. Okay? So in order for an up-up-down to exist, we have to use the three primary colors. So the three primary colors being red, blue, and green. Okay? So that configuration of up-up-down, which I should erase something in order to get to it. I'm going to erase my leptons. Oh no, there goes half the universe. To talk about quarks. Okay? So that proton was up, up, down. We have a spin up, a spin down, and then my down can be either a spin down or a spin up. It doesn't really matter. But now I have an issue where I have Pauli's exclusion principle violated. So what we do is we say this one is red. It's an up red. This one is an up blue. And this one is a down green. So now I have a red and a green. They have different energy states associated with them. Therefore, I'm not in violation of Pauli's exclusion principle. Okay? So I have the spin configurations for my up and my down, and I have my color configurations for, my spin configurations for my up and my up, and I have my color configurations for my up and my down. So now I've created a particle called a proton that doesn't violate Pauli's exclusion principle. Okay? Does that make sense? So that's how you make a proton. How do you make an antiproton? Well, an antiproton is the same thing. It's an up, up, down. But instead of up, up, down, it's the anti-up, it's the anti-up, the anti-up, anti-down. Now, a spin configuration can stay the same. It's not all that important. But when it comes to color, they have the anti-colors. You can hardly see it on the blue. Let me darken that. Okay? Cool? So, this being my antiproton, it has anti-red, anti-blue, anti-green. Okay? It doesn't have magenta, cyan, and yellow. It has the anti-red. Cool? So that's a proton. Now how will we build a neutron? Well, constructing a neutron, well, we know that a neutron has zero charge and a half spin. So using my first generation particles, if I go down, down, up, okay, down and down give me -1/2, -1/2. Up gives me, or not -1/2, -1/3 plus -1/3, -2/3 plus a 2/3 gives me 0. I've got my charge. And because I have two downs, my spin can take that configuration and I get my half spin. Okay? Now the anti of that, well, here we go. Forgot my red, blue, green. Because I need to be able to separate this one and this one because my spins are in trouble. Now if I go ahead and I want to make the anti of that, it's anti-down, red, anti-red. Okay? That's the anti-neutron. So Does a neutron have an antiparticle? Most certainly. It looks like, for all intents and purposes, like the real particle. If I were to make an observation of this, this could have a half spin or it could have a negative half spin, much in the same way that the neutron has. It has the exact same charge. It has 0. So, excuse me, the reason why the neutron is an antineutron is because it's made of antiquarks. Okay? Cool? So, makes sense? Now, what we need to do is we need to also come up with a way in which we can count particles. So we're going to come up with a way in which we can count particles. So how we're going to do that is we're going to say every quark counts as a third. Okay? Every quark counts as a third. So if I use 3 quarks to put it together, I get 1. Okay? And that is referred to as Byron number. Okay? Cool? So, when we're dealing with hadrons, which are these quarks made of 3, we add them together and we get 1. If it's an antihadron, if it's made of antiparticles, it's not 1/3, it's negative 1/3. So that number is 1. Or not 1, the negative 1. Okay? So I get my positive 1, I get my negative 1. Cool? So it turns out to be an integer. Now, is there a way in which I can get another value other than 1 dealing with this idea of adding 1/3 and subtracting 1/3? Yeah, there is. And there's a way to do it that doesn't violate any of our laws. Okay? So, what I'm going to do is I'm going to make a particle out of up and negative down. Okay? So, the spin configuration is going to be up and down, so there's no spin to it. Excuse me while I erase that. But because we added blue and green and blue, green, and red together to get a complete particle. So when you add those together when you're dealing with light, you get white. So, or most people just say no color. What I need to do is be able to make this so that there's no color. So what I'm going to do is I'm going to add a U, an up red, to an anti-down anti-red. So the color of that is still no color. You add a red to an anti-red, you get nothing. Okay? So I have my spin configuration, whichever way I want it to be, resulting in a 0 spin, excuse me. I have my color configuration in a way in which I have no color. Now if I was going to add these to get my baryon number, I have 1/3 minus 1/3. A quark and an antiquark adding together. So numbers for this kind of configuration are 0. Okay? Cool? Now this particle isn't a hadron, it's what's called a meson. M-E-S-O-N. Meson. So of these types of particles, we have our hadrons, which are 3. We have a meson, which are 2. And theoretically, there's a 4 and a 5 out there, though I haven't heard any news of anyone discovering them. So for now, we're only going to be concerned with 2. Cool? Now, talking about the quarks themselves. Oh, I better stop. This is 19 minutes.